Welcome! In today's video we are going to talk about parameter integrals as a mean of actually computing integrals of functions over boxes in higher dimensions. The basic idea is, if we have given a function over a box, then of course we could try to integrate that function first with respect to, say, x1, then with respect to x2, then with respect to x3, and so on, until we have integrated over all the possible variables in turn. The question here is, of course, does that strategy lead to the correct result? Or under what conditions does that lead to the correct result? And we're going to investigate that question today. So let's first make a quick note of that idea before we proceed to investigate it. So for an integral over a box, we could try to integrate over x1 first, then integrate the result over x2, and so on. Reducing by one variable per integration step. And the question is, of course, would that lead to the correct result? Would that lead to the actual integral? And under what conditions would that lead to the actual integral? Now, before we investigate that conditions, let us first define that idea more precisely. And here's the definition of what we call a parameter integral. Now, of course, the order in which we treat the variables is more or less arbitrary, right? We can start with x1, then do x2, or we could do it in the other direction. It's pretty much arbitrary which variable we start with. So we'll define that independently of the variable, and that makes that definition a little longer, unfortunately. So we'll start with a box as usual. So let B equal to BAB be a box in R to the n. And for the notation, we'll say that A is the vector that consists of the components alpha 1 to alpha n. And similarly for B, that consists of the components beta 1 to beta n. And then let's have a function on that box. So let f be a function defined on B with values in R. In the following, we need to eliminate one of the variables, one of the entries from the vectors, and we'll define a notation for that. So we'll say for I in the set 1 to n, we'll define A minus I and B minus I as the vectors where the ith coordinate is missing. So these denote the vectors a minus I, that is defined as the vector alpha 1 to alpha I minus 1. Then the ith coordinate is missing, and we'll continue with alpha I plus 1, and then the others up to alpha n. Okay, so that's a vector with one coordinate less than the original one there, so it's in Rn to the minus 1. And b minus I is defined in the same way. We just take all the coordinates up to the I minus first, then we just leave out the ith coordinate, start again with the I plus first, and then proceed to the last one. So just remove coordinate I from the vectors. Okay, and with this notation we can then define a function that we call the parameter integral. Basically what we want to do is we want to integrate with respect to this xi, the ith variable, and that's what we call this parameter integral here. Okay, so then the function, we call that capital F I, and that is defined on a box a minus I, b minus I. That's why we need those minus I vectors. So we just leave out one coordinate from the box definitions. That's again a function with real values. And it's defined as fi of x1 to xi minus 1, xi plus 1 to xn. So there's one variable missing from that function, because what we do is we integrate over that variable xi. And we'll integrate that from alpha I to beta I. F of x1 to xn. And we integrate that with respect to the variable xi. So integrate over just this one variable, use the limits for this one variable, and then you get a function that is dependent on one less variable, and that's what we call the ith parameter integral. Okay, so this is called ith parameter integral of f. And of course that function need not necessarily exist. That all depends on the integrability of f as well. So if it actually exists. Okay, so that's a somewhat abstract definition, but it's actually pretty easy to execute. So let's see a quick example, just as an illustration of what we mean by the parameter integral. So as an example, let's consider the function f of x1, x2 is 2 minus x1 minus x2. And we'll consider the box 0, 1 squared. Then the first parameter integral, f1, that means we're integrating over x1. That means we are left with the variable x2. Okay, so that function depends just on x2. We're integrating over x1, and I'll usually denote the variable of integration at the limits as well. So we're integrating x1 from 0 to 1 of that function, 2 minus x1 minus x2 dx1. Okay, so this is that first parameter integral. And of course that can easily be computed. That is 2x1 minus x1 squared over 2 minus x1 x2 for x1 from 0 to 1. So what we get here is, so the upper limit is 2 minus 1 over 2 minus x2 minus, and the lower limit is just 0. So we get 3 over 2 minus x2. Okay, so this is the first parameter integral, or the parameter integral with respect to x1 of that function. And just for comparison, let's also compute f2. That will then depend on x1. Right, now we're integrating out the x2 variable. So this time the integral is x2 from 0 to 1. The box is from 0 to 1 in both directions, so that doesn't make a difference for the limits. 2 minus x1 minus x2 dx2. So this time it's x2, okay? The integral is almost the same. It's 2x2 minus x1 x2 minus x2 squared over 2, x2 from 0 to 1, and the result that we get is 2 minus x1 minus 1 over 2, and again minus 0. So we got almost the same result. It's 3 over 2 minus x1 this time. So that's the second parameter integral for that function, small f here. Okay, so as you can imagine, if we integrate these capital F1 or capital F2 once more with respect to the remaining variable, then we get a value, a real value. And the question is, when does this actually represent the value of the integral? And of course, the question is also, does the order of integration actually matter? So is F1 and then integrate that over F2? Is that the same thing as F2 and then integrating that over x1? And the answer to that question is one of the most important theorems in integration theory. That's Fubinis Theorem. That basically says this works for certain types of functions, namely for functions that are continuous on their domain. There are several generalizations of this theorem, but we'll only be concerned with that easy version here. Okay, so the statement is a little complicated to express, but it's actually easy to apply. Let's write down the expression first. So again, we'll have a box. Let B of AB be a box in R to the n. Be a box, and F BAB to R be continuous on that box, on BAB. And then what that theorem says is two things. First, the parameter integrals, the capital Fi, are then also continuous on their respective domains. So the parameter integrals Fi are continuous on their domains, which is B A minus I, B minus I, for all I. And that means the result can be integrated again and again. Fubinis theorem will hold because the function we put into the integral is continuous again. So that whole process can be repeated. And the center of the theorem is now that second statement here that says it doesn't matter in which order we apply these parameter integrals. Whatever order we choose is fine and will yield the correct result, namely the actual integral of f over the box. And to express that, we'll need a permutation of the indices to express that order. So we'll say let pi be a mapping from 1 to n to 1 to n, be bijective. Such a mapping is called a permutation. Basically that means we take the numbers 1 to n and we just reorder them. We permute them in any way we want. But every number appears exactly once in that reordering. Okay, so we have this permutation. And then the statement of the theorem is the following. The integral of f of x dx over the box BAB is the same as integrating, so as the repeated parameter integrals. So let's say the outer integral is the one over the variable pi 1. So we're integrating over alpha pi 1 to beta pi 1. Then we're integrating over variable pi 2. And remember that just means any variable from 1 to n. And so on, up to the innermost integral. The innermost integral is then variable pi n. F of x1 to xn dx pi n, and so on, dx pi 2 dx pi 1. Okay, so basically what you do is you order the variables x1 to xn in any order, and you integrate successively from the innermost to the outermost in any order you want. The result will be the correct integral value. Okay, so that's what this theorem says. Okay, so in other words, for a continuous function, on a box, B, the integral f of x dx over the box B can be computed through successive parameter integrals in arbitrary order. Okay, so that is the main statement here. As long as the function is continuous, parameter integrals will work seamlessly, and you can choose the order that you want, that you prefer for whatever reason. Okay, so that gives us a means of actually computing these integrals in an easy way, because all we need to do is we need to be able to evaluate one-dimensional integrals. A parameter integral is basically just that, a one-dimensional integral, and we just need to repeat that process until we have our actual integral value. We'll see some examples of that in one of the next videos, and then we'll explore other means of integration as well.